Okay, everybody, and welcome to this webinar. It's a very great pleasure for me to be able to open this today. It's now a couple of minutes past 3 o'clock in Danish time, and I know that you're sitting around the world listening to and watching this webinar. And it's difficult to imagine what time it is in the day where you're sitting, but let me proceed. So we will keep on time. On behalf of Dagang Lu and Jin Jun Chin and Min Liu, Wei Heng Xiang, and myself, welcome to this webinar. I would very much like, first of all, to give my warmest thanks to all of you sitting around the world participating in the webinar, and of course also very much to our colleagues who will give presentations in the webinar here over the next months, and maybe especially a thank to Min Liu and Wei Heng Xiang from HIT for their great work in supporting the organization of the webinar, and of course also all the organizations supporting the event, and that includes the Joint Committee on Structural Safety, the Joint Committee on the Globe Consensus, Harbin Institute of Technology, Shanghai Jiao Tong University, and Aalborg University. So a little bit of practical information. As you may have seen from the program, we have in this webinar 14 web events, whereby 13 are lectures, and in the end we have one panel discussion. And hopefully you have already found the link to the homepage where you can find information about the webinar and the program. So have a look at this link here. It contains the program for the webinar with the dates and the times of the lectures. Please note that the lectures are generally given mid-afternoon in the time zones of the presenters. And we have done that to accommodate for the possibility for people attending in the same time zone of the people who are presenting. Of course, everybody can attend, but for some people it will be night when it's afternoon where the presenter is. So that's why we did it like this. And 1 week ahead of each lecture, you will find an abstract of the lecture and a biography of the presenter on this homepage. And also 1 day after each lecture, you will find the video of the lecture from the day before. So you can always find this material on the homepage. At the end of each webinar, we will shortly announce the next presenter and the lecture, and also after each lecture we will address questions and comments, which you are very, very welcome to write in the chat during the lecture. Let's see how many questions or comments there will be. Otherwise, if there are some issues which we are not able to address in the time of the webinar event, you are most welcome also to exchange per email, and we will be very happy to engage in discussions with you. We aim for limiting lectures to a duration of 45 minutes or so that we have time for the Q&A sessions. And one important note is also that we are recording the webinar. And that also means that from the recording we will have a record of who is attending, and it's my duty to let you know that by participating in the webinar, you also agree with us recording the lectures and your presence. So I will start the webinar series. So this is the first lecture. As usual, I have probably too much material, why I have to be a little bit fast on some of the slides. But you are, of course, able to pick up the presentations and the videos from the homepage after the lecture tomorrow to have a closer look. My presentation here concerns the general aspects of risk resilience and sustainability of infrastructure systems. And let me just see if I can make it shift. Yeah, oops. I will talk about the role of infrastructure systems in society to start out with, and underline some important contemporary challenges. Then I will talk about integrity management in more general terms at a high level. Then I will address the modeling and analysis of risk, resilience, and sustainability for systems in a more general sense, but of course it all applies for integrity management of infrastructure systems. I will, if time allows, I will have a look at a couple of examples. Then I will give you some conclusions and outlook, and then in the very end, I will give you an overview of the webinar and share a little bit of our considerations on how we have structured the webinar. So, as you probably appreciate, infrastructure systems have played a very crucial role for the development of civilization as we know it today. It starts several thousand years ago, and we have had developments over time quite rapidly, but of course over the last couple of hundred years, where the population on Earth has increased rapidly, as you see in this figure here, the amount of infrastructure has developed correspondingly. So we are now in a very different world as compared to the time of the pyramids of Giza. The infrastructure, the development of infrastructure and the maintenance, integrity management of infrastructure, the role of these activities is illustrated in this figure here. The fundamentally infrastructure provides a means for production in society, and the production in turn is the basis for the economic developments. And the economic developments in turn are crucially important for increasing, developing life safety and health. And that is of crucial importance for the human capital, which again feeds into the production. Now, these mechanisms are well known, but it's also well known that the development and integrity management of infrastructure systems necessitates natural resources. So this is where we get the materials and the energy from. And we also, when we do that, we are imposing on the environmental qualities, so the boundary conditions for our civilization. And infrastructure systems are quite significant. It's a major thing in society. We are presently accommodating for around 8 billion people, and we have more than 500 cities in the world with more than 1 million inhabitants, and many of these cities, they have much more than 1 million inhabitants actually. There's a huge number of bridges alone in the United States, more than 600,000. The global road network is above 13 million kilometers. We have significant amounts of rail network, airports, offshore platforms, and so on and so on. We are talking about really big numbers. The development of infrastructure systems and the development of the economy in our societies are strongly correlated. So from macroeconomics, it's well known that the development of infrastructure is a means for improving, enhancing economic developments in societies. And it's also well known that if infrastructure is deteriorating and not functioning properly, then economy will also suffer. We also see that there's a strong development between economy and welfare. So the life expectancy at birth is strongly influenced by the level of economic development. And you see here for around 200 nation states in the world, you see the tendency how the GDP per capita is correlated with life expectancy at birth. So infrastructure development and integrity management is a key player in the development of economy and welfare on the globe. There's also a dark side we have realized within the later years, and that is that the development of the amount of infrastructure and the economy alongside in parallel is strongly related to the level of emissions of greenhouse gases. And this is a critical point. This is a point I would like to talk a little bit more about. We know that infrastructure systems, when we look at all infrastructure systems, are responsible for around 80% of global greenhouse gas emissions. As the UNOPS and UNEP and the University of Oxford, they have published. We also know that the embedded CO2 from construction alone, this is not related particularly to the activities of the infrastructure systems, but alone from constructing the infrastructure systems and keeping them running for their services. That is around 20% of global greenhouse gas emissions. So the built environment and infrastructure systems are also key players when it comes to focus on how to reduce CO2 emissions and thereby also to reduce climate change and the negative impacts of climate change. The built environment is a very important constituent of infrastructure systems, contributes with around 10% of GDP if we look at Europe, but the number is not much different from many other parts of the world. So it is even just as a sector a very important contributor to development of economy. But it's also responsible for about 50% of global energy consumption. And if we just look at concrete or cement, is responsible for about 8% of global CO2 emissions. The built environment is also responsible for about 90% of global material consumption. So the materials cycle of the built environment and the infrastructure that the built environment supports is huge. It's one of the most important of all in society. And the future demands will be quite significant. If we look at the development within the decade we already are in, from 2020 to 30, it's estimated that the number of square meters on the roof will double globally. And just as a waypoint, the consumption of concrete in China over the last 3 to 5 years amounts to the same number as the total consumption of concrete in the North Americas over the last 100 years. And this is not because they're doing things bad in China at all. It's just an indicator of how developing parts and rising economies in the world also needs consumption of materials and development of infrastructure. And of course, this is not going to change much in the coming years. And just as an example, it's estimated that the demand for urban housing in Africa will increase by a factor of 5 between now and 2050. So the challenges are enormous if we want to reduce emissions of CO2. development of infrastructure and integrity management, which is the focus of this webinar here, is important because the infrastructure systems, they are subject to degradation due to various processes such as corrosion, fatigue, and just wear. They also suffer damages due to various types of accidents, collisions. They are subject to natural hazard events like earthquakes, floods, and hurricanes, and the like. And also damages due to, of course, just extreme operational loads. They can also, and this happens quite often, be subject to change of use. So over time, operational loads tend to change quite significantly, and quite often it's an issue that lifetime extensions are wanted or required. Here in the later years, of course, we also enter the situation that we need to adapt due to climate changes, and altogether we need to minimize CO2 emissions. So these factors are quite important for the need of integrity management. And what can we actually do? Well, we can keep an eye on the development of how the infrastructure is doing by inspection and maintenance, monitoring, structural health monitoring. We can intervene with repairs, strengthening, and renewals if we need to rebuild. We can definitely also constrain the use of the infrastructure systems. And if we are looking at infrastructure systems like bridges, it's easy to understand that load control can be one means also of managing the integrity, but also limiting the consequences if something should go wrong, consequence control. And the idea for integrity management, just on one slide, is that we base the decisions for integrity management of models. And those models are on our desktops. We can call them models of the real world. However we formulate these models, we can relate the models on our desktop with observations from the real world. And we do that through the concept of indicators. So we are simply modeling our knowledge and our models of reality in a way that we can take benefit of everything which can be observed from the infrastructure systems for which we are doing integrity management. And then using our models, we identify good or even optimal decision alternatives for the integrity management. And then, of course, we implement them finally into reality. It's important to have a lifetime perspective when we do the integrity management. And here, lifetime is not dedicatedly focusing on the lifetime of the individual objects in the infrastructure systems, like the lifetime of a bridge, one particular bridge. We need to look at the functionality and the duration where functionality or service from the infrastructure is required. And then we need to have a focus on all the repairs, all the integrity management actions which we can take within that period of time, including repairs, inspections, monitoring, renewals, and so on over time. So it's like a sequence. It's a repeated sequence of events over time, with taking place at times as needed, depending on what happens to the infrastructure over time. And of course, when we design and we optimize integrity management, this is a process that we need to account for. And we need to find a good balance between decisions on design and decisions on integrity management. And the typical approach to that, as it is at present, is that first we make design decisions for our infrastructure systems, And then the infrastructure systems go into the operational phase, and then experts on integrity management take over, and they do the best they can to keep the systems up and running with the required reliability in a optimal manner. But this is not a good approach. We need to integrate these two steps, taking benefit of the interaction between design decisions and integrity management decisions. So we need to change, let's say, these best practices so that design decisions and integrity management decisions are decided jointly and at best optimally. When we look at individual infrastructure systems or components like a bridge illustrated here, we also need to have a look at the different phases during the lifetime of such an individual component, and that goes through the idea and concept over the planning to local site investigations, design, manufacturing, execution, operation and maintenance, and finally decommissioning and recycling or reuse of materials into the next step in the lifetime, as we saw in this slide here. So we need to think holistically. And when we look at portfolios of infrastructure components or systems, we also need to have a look at the possibilities for optimizing at the level of regulations and codes, or in other words, best practices. And doing so, we of course need to have a close look at economy and safety, but maybe even more so at the environment and emissions. I would like to talk about concepts of or characteristics of systems, and we very often talk about safety risk and robustness. In the later years, 10 or 20 years, resilience has come up, and sustainability is of course with increasing importance coming into the picture, as we all know right now, and why. So risk, safety really serves to help us choose among options in the face of uncertainty in more general terms. Whereas robustness and resilience addresses how to maintain functionality service over time. And sustainability relates to how to maintain preferred balances in the long run. And these balances are of course related to the boundary conditions for our activities on the globe, both at global scale and local scale. When we look at the overall system representation, I just want to show you this figure here from the Joint Committee on Structural Safety, where we split up so we don't have too much focus on the procedures on how to manage risk. This you can find good procedures in many codes, not least the ISO codes, but that gives you not too much understanding about the systems that we are modeling. And this way, which is shown here on the screen, we are splitting up the system into what we call exposure events or hazard events. We are looking at the individual constituents of the systems that we are addressing, trying to model. And we look at the failure or damage events and the consequences associated with these individual failures of constituents in our systems or damages to these. We relate to what we call direct consequences. And then what happens with respect to the functionality, that is the services provided by the systems comprised by these constituents due to the performances of the constituents, the damages and failures, we relate to what we call indirect consequences. And let's say the relationship between exposure or hazard events and the direct consequences, this is what we term vulnerability, and the link between the direct consequences and the indirect consequences is what we relate to the concept of robustness. So essentially, if consequences stop at direct consequences, then the system is perfectly robust. But if indirect consequences are very significant compared to direct consequences, then the system is lacking robustness. And of course, when we are modeling systems, we also need to take into account the backcoupling effects. So when we have damages and failure events within the constituents of the system has to reallocate, it has to distribute or reorganize the internal demands in the system. And in some cases, this leads to follow-up damages and failures, and even to cascading failure of the system as such, and total loss of functionality. And that most importantly has to be accounted for. When we are modeling risk, traditionally we have a focus on losses, but that doesn't fly if we want to model resilience and sustainability also, because resilience and sustainability has to be seen relative to the benefit or the services provided by the systems. So we need both to look at the income side and then on the loss side when we are addressing resilience and sustainability. We can look at systems at different levels, and we have to do that. There's a general principle on the granularity, how to choose the granularity in your risk modeling and your systems modeling. And the rule is that we need a representation which facilitates that we can differentiate the expected value of benefit associated with the different decision alternatives. And this is like the only really strong rule for choosing the granularity. And it's an adaptive approach where you have to try to find the right scale given the situations that you're trying to support by risk-informed decision making. So at one scale, the constituents of a system can be individual bridges in a road network. So the overall system is a road network and the constituents are bridges. But if you look at the bridge as a system that you're addressing, then for instance, the cables or the pylons would comprise the constituents of that system. If you just look at the cable, then the constituents of the system that you're addressing could be the individual wires. But the overall modeling is the same. And of course, it also combines across scales. The one important message is that decision analysis is the Bayesian decision analysis is a formal framework for ranking decision alternatives. And of course, we will not be able to go through the details of this here. I just want to illustrate that in many cases, we can be in doubt about the actual configuration of the system. In some cases, can I ask to mute? Thank you. Yeah, so in some cases, there can be competing system models, and we then have to ensure that our decision-making accounts for the possibility of different competing system models, and this can also be facilitated. That may sound a little bit strange, but for instance, if you are planning the development and integrity management for an infrastructure system, and we are dealing with models for climate change, then as you all know, that there are different scenarios for the climate change of the future. In the IPCC, they relate to these different models as different scenarios depending on societal developments. And of course, we need to take into account the possibility that society, global society, will develop in different ways when we are planning infrastructure and integrity management of infrastructure for the next hundreds of years. Value of information, I just want to underline, is a strong means supported by decision analysis for identifying how we can best collect additional information, new information about the performance of the infrastructure systems as a means to improve our models and be better at ranking decision alternatives. This is a very strong framework for deciding on where to make tests, what models to improve, and how and where to monitor and inspect. Looking at robustness, I don't want to go through the definitions, but there are different definitions of robustness depending on what science area you're looking at. As already mentioned, in infrastructure systems, it gives good meaning to differentiate direct consequences and indirect consequences, and then relate for the different events of the possible scenarios which will take place over time, the expected value of direct consequences to the expected value of total consequences. That means the sum of the direct and indirect consequences. So that ratio, which you can express in different ways, it's fundamentally what you see here, that for each of the possible scenarios you see here, going from exposure to direct and indirect or follow-up consequences, you can imagine that there will be direct consequences for that scenario and total consequences. And this ratio is a good indicator of the robustness. So if this ratio is equal to 1, then we have a perfectly robust system. Nothing happens after the damages or failures of individual constituents. But of course, these scenarios are outcomes of random processes or random events. Why it makes it makes sense to take the expected value of this ratio over all the possible outcomes of these scenarios, or all possible scenarios. So in order to evaluate the robustness, and as you will see also resilience and sustainability for that matter, we need to be able to model probabilistically the scenarios. We need to have the probabilities that they will take place individually. Looking at resilience, again, there are different definitions depending on what science domain you come out of. Pym and Holling come out of ecology. Cotter come out of socio-systems science. Bono is recognized as one of the first movers in engineering. I tend to like the National Academy of Science, indicating that resilience relates to a system's ability to plan for, recover from, and adapt to adverse events over time. And I would like to highlight that in this definition, the focus on, so it's pinpointed here that we are talking about the system's ability. So we are looking at the system as an entity in itself, and it's the system's ability to plan for and recover and adapt to adverse events over time. And over time is infinite in principle, right? So there's no upper limit given here to the time frame considered. And when we look at resilience and sustainability for that matter also, we need to have a view at the hierarchical organization of governance, because this is where resilience comes in as a central characteristic. We need to understand to what degree at the different levels in the hierarchy, the underlying system will be able to do what they're supposed to do without help from the outside over time. And of course, if you are managing a number of such systems, you're responsible for that. You need to know what risks are associated with this responsibility. So what is the probability that one of these subsystems will not be able to perform or survive, provides its functionality over time without help? Of course, as a responsible, you will be the one, the entity having to decide what to do in case the underlying system fails, in case it's not resilient, right? So this is a framework we are dealing with. And when we are looking at infrastructure systems, of course, we cannot see them in isolation. We need to realize that they are interrelating with social systems, anthropological systems in general, but also very importantly, the geohazard systems, and they also impose on the Earth life support systems. So the boundary conditions for our existence. And that can be at local as well as at global scale. Local scale would be, for instance, toxic events in communities affecting livelihoods. Global scale could relate to CO2 emissions, changing the climate conditions. And when we look at the resilience, there's a typical focus on the figure. As we see here, we have some service provided over time. Then we have a disturbance event taking place at some point in time of a certain magnitude or intensity. And then we have a loss of service over a period of time. But it's very informative to have a look at the capacity actually to re-establish function, how that develops over time. And this capacity develops as time goes by the service, or supported by the service the system itself provides. So when we have a disturbance, then we lose some of this capacity because we need it in order to re-establish the system functionality. After we have re-established, then the capacity grows again, right? The drop in service, you may realize, relates explicitly to robustness. So robustness relates to indirect consequences. So the drop is characterized by robustness. And of course, the shape of the recovery curve depends on our preparedness and adaptive capacity. And now if you look at a scenario where we have different disturbance events at different points in time, a resilience failure takes place when the capacity to deal with a disturbance is no longer sufficient. So when the capacity is exhausted. So this is what we relate to a resilience failure event. So that's quite important. And of course, we can model all this probabilistically, and we can also evaluate the probability looking at all possible disturbance scenarios over time. We can look at the probability that we will have such an event of resilience failure. When we look at the sustainability, of course, the definition of Gro Harlem Brundtland is always quite useful, but how do we actually relate to this in addressing infrastructure systems? We need to look at the environment, social and economic dimensions. Of central importance is the environment, and presently we need to focus on that our actions in developing society at, of course, regional, national, but also at global scale, do not exceed the capacities of the planetary system, also referred to as the global planetary boundaries. So addressing CO2 emissions and climate change, what we can do, and this is the approach that I take, is that I relate to any decision on development and integrity management for infrastructure. We can convert these decisions into elementary flows. So amount of use of material and activities which relates to elements and elements flow, and that can be differentiated so that we look at CO2 emissions, ozone depletion, human toxicity, and noise, and all sorts of effects related to our decisions. So we have to unfold our decision into these elementary flows. Then we can categorize these into different groups depending on their effect to the environment. And Here, I have just illustrated that some of these can be related to the planetary boundary, the capacities for the Earth's life support system. And then we can look at the problem of managing the risks associated or the consequences associated with our decisions, just as we do when we do normal probabilistic engineering decision making, by looking at our knowledge for the capacities as we have here, and our knowledge concerning the loading, that means the effect of these elementary flows caused by our decisions. And with that type of modeling, we can also model the probability that we will have exceedance of the Earth's life system support variables, the planetary boundaries. And of course, the tools for doing this would be LCA analysis for the decomposition into elementary flows, and probabilistic sustainability assessments would be the means for supporting decisions on what decisions to go for. And again, it can be undertaken in the same way as we model resilience, and at global scale, resilience and sustainability is actually the same. When we are looking also ahead into the future, we need to have an appreciation that our decisions at present, they affect future generations or future decision makers. And we need a good scheme for accounting for these effects and also having equity over time. When we are making decisions, we should treat all future decision makers or societies with equal weight as our own generation or ourselves. I cannot go into the details here, but this relates a lot to the discounting that we implement and take into account when we are ranking decision alternatives at time zero. We need a scheme for discounting consequences taking place into the future. And I've indicated some literature where you can find advice on that. There are trade-offs, important trade-offs in the management of integrity, and that concerns trade-off between resilience and sustainability. I want to highlight because there's so much talk that we need to improve resilience of infrastructure systems. Politicians are talking a lot about where we want more and more resilient systems. Also, the engineering community are advocating we need to maximize resilience, but we cannot do that without imposing on the environment. So we need to understand better how resilience interrelates or affects sustainability. It's just like safety, structural safety. The more safety we put into a structure, the more material we will actually use. And the more material we will use, the more are the impositions on the environment. So we need to think how resilient is resilient enough. I just want to highlight that there are a lot of concepts which are actually in play when we are addressing the knowledge domain of risk, resilience, and sustainability. And in order to communicate clearly among professionals across all the sciences which are required to address both risk, resilience, and sustainability for infrastructure systems, we need a common language. And we have one proposition for the conceptual constituents of such a common language, which could be applied in any application domain. A few examples. Well, these methods I'm talking about here, they have indeed been applied in practice over many, many years. Risk-based inspection planning is probably one of the most massive application areas of risk-informed integrity management up till now. But already, already in the early 90s, I was reassessing a very simple bridge where there was doubt about the capacity of the foundation, because the capacity models for the foundation did not really account for the effect of the resistance provided by the piles above the footing of the pile. And this is because the soil is destroyed when you press down the pile to start with, and the driving locks of the piles do not account for the effect that over time, after a few years, the capacity will increase because of the shafts. But taking into that account, it was possible just for this simple little bridge to save 50 million Danish kroner in rehabilitation. Other good examples relate to the reassessment and rehabilitation of the Sarate-Brasolago bridges, where risk-based methods came solidly into the picture, and the risk-informed inspection planning was a key instrument for maintaining the integrity of the structures until it could be fully repaired. Conclusions and outlook. We have a lot of opportunities to improve the way we develop and manage the integrity of infrastructure systems, and we simply have to do it better. We need a radical change in the way we do it presently. And actually, if we are doing as we are doing things now in best practices, if we cannot uncouple growth, which we have not been able to, and resource consumption, then we simply have to build as little as possible. This is a sad fact. We need to use much less materials. We need to use materials with smaller carbon footprints. We need to use all available knowledge on loads and capacities of the infrastructure systems. We need to look at the use of active rather than passive means for safety, because active means typically are much less energy consuming and material consuming, and therefore also have smaller footprints. Structural health monitoring should not be an add-on after the structures and the infrastructure systems have been realized, but it has to be an integral part of design concepts. And we need to take benefit of all possibilities in digitalization and big data technologies. And there are more, of course, but we cannot talk about them here. But there are huge potentials for doing things much, much better. And we don't have time to play around with interesting technologies. Why am I saying that? This is because I see so many interesting research proposals which really will never lead to anywhere except maybe attracting some research funding, but of practical relevance, they will not contribute much. So you need to be critical. You need to be really self-critical in your activities, because we need impact now in the short term. We already know a lot on how to do things better, and we will get very far if we will just implement now what we know. And this requires a global appreciation and coordination, and not least regulatory requirements and economic incentives. Have a look at the Globe Consensus and support the Globe Consensus, where you will find more information in this respect. I'm closing off my presentation here, but I just want to walk you through the webinar in a glance. So today I tried to give you some perspectives, general aspects of risk resilience and sustainability of infrastructure systems, addressing global challenges and potentials. Now, in the next presentation, in several days from now, Helmut Wenzel, who is a well-known practitioner and researcher, also in structural health monitoring, he will give you some perspectives on industry needs, experiences, and potentials. Then Jin-Yun Chen, Paolo Gardoni, Min Ouyang, and Dagang Lu will be addressing different angles of the modeling or different sides of the modeling and analysis for energy and transportation systems. Ji Li and Yongbo Peng and Dongping Fang and Nan Li will be addressing modeling and analysis at the level of city and urban systems. And then we will go into the technologies and the techniques by Daniel Straub, Yunho Song, Eleni Shetzi, and Jürgen Hagel. And finally, we will have a closer look into the more advanced present practices from industry, and also some perspectives on the experiences. Finally, we will have the panel discussion, and we will inform more about what that will contain as we get further into the webinar series. So far, thank you for your attention. I know I went a little bit over time, but I hope we can manage that, and I also look forward to some interesting questions from the chat function. If you have not put in your questions by now, then by all means do it. And as I indicated before, you are very, very welcome always to contact me or any of us by email as well. So by this, I would like to stop sharing, and I'm now ready for some questions and answers. Thank you.
Okay, thank you, Michael, for your nice, very nice presentation. I think today's is a ice-breaking ceremony for our webinar series. So next, please, if everybody you have questions, please raise your hand or just type your questions in the chat box. So please, okay, now. Yes, yes. You can ask questions.
Maybe we need to unmute.
Yes. Could I ask one question? I cannot ask the question. Why? I don't know.
And now you can open your microphone.
Yes.
Oh, yeah. Professor Faber, this is Dr. James from the US. It is
Okay.
a very good presentation. I do have one question regarding in the US, we always talk about climate change and resiliency. So I know you talked a lot about resiliency, but how about climate change? Thank you.
Yeah, it's not only in the US. Of course, we talk about climate change and resilience, and you also there's a strong coupling between the climate change, because we need in many cases to adapt our infrastructure systems such as to accommodate for the climate change that we can imagine will take place in the future. And this is very relevant, but we just need to do it in a careful way, where we think carefully about how we can improve resilience of our infrastructure systems without aggravating the climate change in the future. So just by putting more material and safety and reliability and resilience into our infrastructure systems is maybe not always just a positive thing, because we can also over-consume material. So we need to do it in a smart way. And as I already indicated, the active means for improving resilience and performance of infrastructure systems in general is maybe one we should focus on, so that we can catch potentially adverse events in the future before they actually happen, instead of retrofitting our infrastructure systems so that they passively can take any future changes, right? Does that address your question?
Yeah, thank you.
You're very
Thank you,
welcome.
Jianqi. Thank you. So another question? Michael, can you see?
Yep.
You okay?
Explain the meaning of the capacity and the resilience. Yes, yes. Thank you for this question. So fundamentally, all our infrastructure systems, they are providing services. And from these services, they also support economy. And that means that for a system in itself, if we look at an isolated system, if that, as an example, could make sense, it could be a wind turbine, an offshore wind turbine park system as an infrastructure system. Then in order for this system to make sense altogether, it has to be able to provide the economy for its own continued functionality. So that means that a part of the economy generated by the offshore wind turbine park has to be fed in to the long-term operation of the park. If you imagine that the park generates 10 or 100 million dollar per year, then maybe we need to keep 5 or 10 million dollar per year for operating and maintaining the integrity of the offshore wind turbine park. So that is the capacity. So we simply take out a part of the economy generated by the system as the means. You can imagine we put it in the bank so that we are ready if something happens, if something unexpected happens over the lifetime. And then, of course, if we have not accumulated, this is a capacity, in this example, an economic capacity. If we do not have the capacity, if we do not have the money in the bank when a typhoon hits and we have to reconstruct maybe 40% of the wind turbines, then we have a resilience failure. That was just an example. Did that help?
Okay, Michael, another question?
Then there was one with gas systems. Hang on. Can you give a couple of examples of structural health monitoring systems in lifeline system gas, water, etc., that can be integrated in design stage? Well, yes, of course. If you look at the time of the design and you just look at the dimensions of the pipelines where you want to transmit or transport the gas, then there is a very close relationship between the dimensions of the wall thickness, and the durability. So the time until corrosion may take place, or other degradation phenomena may take place and necessitate that integrity management interventions are made in the system. So it's about finding the right balance between the wall thickness on the one side, which cost a lot of material and also cost money and has imposition on CO2, and then the efforts required to keep control of development of degradation of the system. Of course, also possible implications of failures which may take place if you choose the thickness too low. So this and the possibility actually to go into the system and do inspections once in a while to see how the degradation is evolving compared to the assumptions made during the design. So the more monitoring you have in a situation like that, the better control you have over the actual development of degradation. But of course, the control also costs money, right? And if you end up having a lot of repairs, interventions, then that may actually cause more material consumption and more cost than it would have if you had just designed with more thickness from the very beginning. So it is, you have to look across the design integrity management process to identify what is actually optimal when you look over a long period of time, including maybe several renewals of the system into the future.
Okay, thank you very much.
Michael, another question from.
Yeah. Can you highlight if environmental impact should be considered as boundary or should be considered as objective to be minimized? It goes both ways. So it's both a boundary and an objective to be minimized. On the one side, when we are supporting decisions on activities in a given region, so we are developing typically an infrastructure system at a local scale or relatively local, right? But when we do that, we have impositions on the environmental, the qualities of the environment where the infrastructure system is actually established. And there, these impositions could have impact on qualities of the environment, which relates to the maybe loss of species. Loss of species in turn could affect the livelihoods in that particular geographic domain. It could also be toxicity, which is released into the environment and again have negative effects on the livelihoods. But then, of course, also the effect of what we develop and maintain in terms of infrastructure has these impositions which go to the planetary, if you like, the planetary boundaries. And these planetary boundaries, they are constraints, but they are also in the same way they can be considered to be object to minimized impact. So it's both at local and at global scale that we need to keep these environmental impacts in mind. So we want to minimize environmental impacts for sure.
Michael, another question from Yuchun Tang.
Yeah, let me find it. How to incorporate and model future hazard risks, threats, and low, high impact, low probability, which we don't have enough data to model when conducting integrity management. To realize, look forwarding, resilience goals. Well, if we don't have any knowledge about what can happen in the future, you indicate that we do not have information enough. But the question is, what is information enough? So in this sense, little knowledge and little data gives us high uncertainties. And when we are managing systems looking into the future and we are dealing with high uncertainties, we simply need to take account of the uncertainties. So we need to factor in these uncertainties, and we can do that by probabilistic modeling. And in some cases, we could anticipate events where we would find it extremely difficult to model the probabilities that these events will take place. And in such situations, what we need to do is we need to think in terms of robustness. So we need to try to not focus on the probabilities, but having a look at the consequences. And then to see how we can devise a system such that if these scenarios will take place, that we minimize the loss of functionality with the lowest imposition on the environment and the lowest imposition on cost. So it becomes, when we know very little, it becomes more a robustness consideration. And the more we know, the more we can target and optimize the system. So these robustness considerations are somehow appreciating and accounting for the uncertainties that we do not account for, either because we just want to do things simpler or because we simply don't know. Then there is a question, so how to validate and verify these resilience or risk methods? Well, I may be a little bit in doubt what you mean by validate, because the mathematical foundation is, of course, waterproof. So what it really amounts to is to use the best available knowledge when we are making decisions. And in some cases, this knowledge is not 100% reflecting what will happen in the future. And by formulating our models, that means representing our knowledge consistently. And the way we can do that is to use mathematics. So we simply do the bookkeeping correctly, and we keep track of all assumptions. And we also make sure that that assumptions are adequate. Then we need to formulate our models in such a way that they can accommodate for all new information which can be collected in the future. And that means that models will successively be better and better and better. Now, this, of course, is closely related simply to Bayesian reasoning. So we may start out with a lot of uncertainty and what people refer to as levels of subjective knowledge. And over time, this knowledge converts in a way to more and more frequentistic type of knowledge. Now, we need to identify decisions taking this uncertainty into account, and we do that by ranking decisions according to their expected value of utility, we call it in decision analysis. And this is totally consistent. But what quite often takes place is that when we have made decisions, then we can be surprised that the decisions turned out not to look good. So we could make a decision on strengthening a bridge, for instance, and then 1 year later comes an earthquake and the bridge collapses because the earthquake was simply more intensive than we had assumed. Now, was that because the models were wrong? Or was it a wrong decision? No, absolutely not. If we accounted for all we knew in the modeling and in the selection of the optimal decision, there's no guarantee that decisions which are based on risk information will come out successfully. But they are still the rational decisions to make in the face of uncertainty. So this is super important to keep in mind, and decision makers should not be judged on the outcome of their decisions. They should be judged on the basis for their decision making. And this is totally different, right? So don't strive for always making decisions that will satisfy everybody. We should focus on deriving decisions, identifying decisions which are consistent with the best available knowledge and, of course, the preferences of stakeholders. Yeah.
Great. Thank you, Michael, for your very detailed responses. And we have make the records of all today's lecture. So everybody, you can find today's lecture and also the details of the next webinar information on the GCSS website. And we also make the recording in China by the Bilibili, a very famous website, so you can make the download. So due to the time limitation, and we have passed the ending time, so I think we have stopped here. And thank you again, Michael, for your very nice presentation. And also, we hope to see you, for everybody, see you on next Monday, on September 5. Okay.
Thank you, everybody. And
thank you.
I wish you a wonderful afternoon, morning, evening, night, wherever you are.
Yeah.
See you again.
See you.